Venus rotates backwards. Here's why it matters. Venus spins in the completely opposite direction from almost every other planet in our solar system. Like a rebellious dancer in the cosmic ballet, Venus follows its own unique rhythm, spinning clockwise while others waltz counterclockwise. In the next few minutes, I'll guide you through the mysteries of Venus's backward rotation. You'll discover how its dense atmosphere acts like a planetary brake system, gradually altering the planet's spin. This peculiar rotation isn't just a cosmic curiosity. It connects to broader questions about planetary formation throughout our galaxy. The secrets hidden in Venus's rebellious spin might even hold clues about Earth's distant future that will surprise you. The backwards planet. Imagine two nearly identical twins, born from the same cosmic material, roughly the same size, orbiting relatively close to one another. This is Earth and Venus, often called sister planets due to their striking similarities in mass, density, and composition. But beneath these surface resemblances lies a fundamental difference that has puzzled astronomers for decades. While Earth spins counterclockwise, completing a full rotation in just 24 hours, Venus defies conventional expectations entirely. Our cosmic neighbor takes a staggering 243 Earth days to complete a single rotation, and it spins in the opposite direction. This profound anomaly challenges our fundamental understanding of planetary formation and evolution. When observed from above its north pole, Venus rotates clockwise, contrary to planetary formation models' predictions. Astronomers call this retrograde rotation, standing in stark contrast to the counterclockwise or prograde rotation exhibited by most other objects in our solar system. To appreciate this mystery's significance, we must understand the standard model of planetary formation. Our solar system began as a vast, rotating cloud of gas and dust. As this nebula collapsed under gravity, it flattened into a spinning disk with the proto-sun at its center. Conservation of angular momentum. The same principle making a spinning ice skater rotate faster when pulling in their arms dictated that this disk would continue spinning in the same direction. Planets, including Venus, formed from material within this disk and should have inherited its rotational direction through the accretion of particles already moving that way. It resembles how water naturally swirls in a consistent direction flowing down a drain, a fundamental physical principle at work. Yet Venus somehow ended up spinning the opposite way. This represents a dramatic deviation, equivalent to a car driving backward against highway traffic. Physically speaking, such a reversal should be highly improbable without some dramatic intervention. Visualize Earth spinning counterclockwise, completing a full circle every 24 hours, creating our familiar day-night cycle. Now imagine Venus, slightly smaller but similar in mass, moving agonizingly slowly in the clockwise direction. On Venus, a single day outlasts an entire Venusian year, a cosmic oddity where darkness lingers and daylight stretches beyond comprehension. The planet completes a rotation in 243 Earth days while orbiting the Sun in just 225 Earth days. This retrograde rotation remains exceedingly rare in our solar system. Among planets, only Venus and Uranus exhibit this pattern, though Uranus's case differs. Rather than spinning backward like Venus, Uranus is tilted on its side at about 98 degrees, essentially rolling along its orbital path with poles alternately pointing toward and away from the Sun. Scientists remain puzzled by Venus's motion because it contradicts fundamental principles that should apply to all planets formed from the same rotating disk. Angular momentum conservation dictates objects should continue moving in the same direction unless acted upon by an external force. For Venus to spin backward, something significant must have occurred, powerful enough to overcome the planet's original rotational momentum and reverse it completely. Venus likely began with rotation similar to Earth's, counterclockwise and relatively rapid. Whatever caused its current retrograde rotation must have happened after the planet had already formed. This anomaly forces planetary scientists to question fundamental assumptions about planetary system development. If our basic models can't account for Venus's rotation, what else might they be missing? What other aspects of planetary development remain poorly understood? The implications extend beyond Venus itself. As we discover thousands of exoplanets around other stars, understanding these anomalies becomes crucial for interpreting observations in distant solar systems. If we don't comprehend variations possible within our own cosmic neighborhood, how can we accurately interpret data about planets orbiting distant stars? Venus's backward rotation suggests a dramatic event. In its past, perhaps a massive collision with another large body, or complex gravitational interactions with the Sun and other planets that gradually reversed its spin over time. These possibilities create fascinating research avenues actively pursued by planetary scientists today. What makes this compelling is that Venus wasn't always the inhospitable world we see now. Evidence suggests it may once have had conditions similar to early Earth, possibly even with liquid water oceans. Understanding how and why Venus's rotation reversed might provide crucial insights into its transformation from a potentially habitable world to the scorching pressure cooker planet we observe today. When spacecraft measure Venus's rotation, they detect its backward spin and extraordinarily slow pace. At Venus's equator, the surface moves at only about 4 miles per hour, compared to Earth's equatorial rotation speed of roughly 1,000 miles per hour. This sluggish rotation profoundly affects the planet's climate and weather systems. While Earth's rapid rotation helps distribute heat evenly, Venus's slow backward rotation creates extreme temperature differences between day and night sides. However, Venus's thick atmosphere counteracts this through powerful winds that circulate much faster than the planet rotates, creating a uniform surface temperature. This peculiarity exemplifies how Venus defies expectations. Its atmosphere rotates much faster than the planet itself, completing a circuit in just 4 Earth days, another phenomenon called superrotation that scientists still work to fully explain. For astronomers and planetary scientists, Venus represents a critical test case for theories of planetary formation and evolution. If our models can't account for Venus's rotation, they're incomplete or possibly fundamentally flawed. This drives renewed interest in Venus missions, with NASA and the European Space Agency planning new spacecraft to study this enigmatic world. Cosmic collision theory. While those future Venus missions prepare to launch, scientists have already developed a compelling theory to explain Venus's peculiar rotation, one that involves violence on a truly planetary scale. The leading explanation for this astronomical oddity centers on what planetary scientists call the giant impact hypothesis, a cataclysmic collision that would dwarf most cosmic events in our solar system's history. This cosmic collision represents a pivotal moment in Venus's history, a singular event that transformed the planet's fundamental motion and set it on a different evolutionary path from Earth. According to this theory, a massive celestial body, perhaps a protoplanet or large asteroid, slammed into Venus during the solar system's formative years. The collision was of extraordinary magnitude, powerful enough to fundamentally alter the rotational momentum of an entire planet. Computer models suggest this impact would have delivered approximately 1.64 times 10 superscript 3 superscript 1 joules of kinetic energy, transferring an angular momentum of about 1.99 times 10 superscript 3 kgm superscript 2/s, figures that represent almost unimaginable cosmic violence. To comprehend the precision required for such an event, we must understand the physics of planetary rotation. Any object striking Venus would need to hit at precisely the right angle and with sufficient force to overcome the planet's existing rotational momentum. Think of it like hitting a spinning top. You need to strike at exactly the right spot and angle to reverse its direction. Simply hitting it anywhere won't change its spin direction. The impact must apply torque in the perfect way to first stop the existing rotation and then impart new momentum in the opposite direction. This scenario bears some resemblance to the impact theory of our moon's formation, where Mars-sized object called Theia collided with early Earth. However, Venus's collision would have needed to transfer enormous angular momentum directly to the planet itself, completely reversing its rotational direction rather than primarily ejecting debris. Computer simulations have been particularly revealing about the specifics of such an event. Models suggest the impactor might have been a proto-Mercury-sized object that struck Venus at a shallow angle. Interestingly, some scenarios indicate that if the collision was grazing enough, a significant portion of the impactor could have escaped Venus's gravity after transferring its momentum. This raises a fascinating possibility. The object that reversed Venus's spin might have reformed into what we now recognize as the planet Mercury. Other simulations suggest alternative fates for the impact debris. Some material might have been captured by the sun's gravity, falling into our star over time. Other fragments could have contributed to Venus's already substantial atmosphere, potentially explaining some of its unusual atmospheric properties compared to Earth. Timing plays a crucial role in this hypothesis. Most planetary scientists place this theoretical collision within the first billion years of our solar system's formation, during what's called the late heavy bombardment period. This era, roughly 4.1 to 3.8 billion years ago, saw intense asteroid activity throughout the inner solar system as gravitational interactions with the giant planets sent countless objects on collision courses with the inner planets. During this chaotic period, impacts were common, though few would have been large enough to alter a planet's rotation. The specific impact that potentially reversed Venus's spin would have been exceptional even by the standards of this violent era. The precise mechanics would have required an object with both substantial mass and the perfect trajectory to deliver its angular momentum efficiently to Venus. One of the most significant challenges to the impact hypothesis is the conspicuous absence of evidence. Unlike the Moon with its visible impact basins or Earth with its geological scars, Venus shows no obvious surface signs of such a catastrophic collision. This absence presents a significant puzzle for scientists. Where is the evidence of an impact powerful enough to reverse a planet's rotation? The answer likely lies in Venus's unique geological history. Unlike Earth, Venus appears to have undergone a global resurfacing event approximately 500 million years ago. This dramatic episode effectively repaved the entire planetary surface, erasing any visible evidence of ancient impacts. The planet's extreme surface conditions, hot enough to melt lead, combined with its active volcanic processes, would have obliterated any impact basins that might once have existed. Furthermore, Venus's dense atmosphere makes studying its surface challenging. The thick clouds of sulfuric acid obscure direct visual observation, requiring radar mapping to see the surface at all. These practical limitations have hindered scientists' ability to search for subtle evidence that might support the impact hypothesis. Despite these challenges, the impact theory receives support from several aspects of Venus's current state. The extreme tilt of Venus's rotational axis, which has the planet spinning nearly upside down compared to most planets, aligns with what we would expect from a massive collision. Additionally, Venus's remarkably slow rotation rate makes sense in this context. A glancing impact would have imparted residual angular momentum that gradually slowed over billions of years. For the impact hypothesis to hold true, scientists must determine precisely what type of collision could achieve the necessary rotational change. The angle would have been critical, too direct, and the impact might have shattered the planet rather than changing its spin. Too shallow and insufficient momentum would have transferred. Computer models suggest the impact would have needed to strike an angle between 10 and 30 degrees from horizontal to achieve the right balance of energy transfer and planetary stability. The giant impact hypothesis remains the most scientifically compelling explanation for Venus's retrograde rotation, but it's not the only theory scientists have proposed. Alternative explanations include complex gravitational interactions with the Sun and other planets, or unique atmospheric tidal coupling mechanisms that could have gradually altered Venus's rotation over billions of years. The tidal locking hypothesis. Those atmospheric tidal coupling mechanisms scientists propose aren't just technical jargon. They represent a cosmic tug-of-war that Venus is currently losing. The Sun pulls one way, Venus's atmosphere pushes another, and caught between these massive forces is a planet whose rotation defies our understanding of how solar systems should behave. The interplay between a planet and its star creates a phenomenon known as tidal locking. When a celestial body becomes tidally locked, it always presents the same face to its parent star, much like our moon always shows the same side to Earth. This occurs because the gravitational pull of the larger body creates a bulge in the smaller body, and over time, this tidal force slows the rotation until one side permanently faces the source of that gravitational pull. For planets close to their stars, like Venus, the Sun's gravitational influence exerts tremendous force. Venus should have become tidally locked billions of years ago, with one hemisphere perpetually facing the scorching sun and the other in darkness. Yet something intervened, something powerful enough to prevent tidal locking and push Venus into a backward spin. The answer appears to lie in Venus's extraordinary atmosphere, a dense, turbulent system that actively engages with the planet rather than passively surrounding it. Stephen Kane, an astrophysicist at the University of California, Riverside, offers a crucial insight that reshapes our understanding of Venus's physical nature. The atmosphere is deeply integrated with the planet, Kane explains, challenging the conventional view that treats atmospheres as separate entities. His research demonstrates that Venus's atmosphere influences nearly every aspect of the planet, including its rotational speed. This perspective marks a significant shift in planetary science, especially when studying worlds with substantial atmospheres like Venus. The atmospheric dynamics create a battle of titans between solar gravity and atmospheric motion. While Venus itself rotates slowly, its atmosphere behaves differently. Powerful winds drive the atmosphere around the planet every 4 Earth days, a phenomenon known as atmospheric superrotation. This rapid circulation creates substantial drag as it interacts with surface features, pulling against the Sun's gravitational influence. This creates a fascinating counterbalance. As solar gravity attempts to lock Venus into position, the fast-moving atmosphere acts as a countervailing force. The result is a complex dance of competing influences that prevents Venus from becoming fully tidally locked while contributing to its unusual retrograde rotation. Mathematical models suggest Venus experienced a transitional phase in its rotational history. The planet likely began with a typical prograde rotation, then gradually slowed as solar tides worked to lock it in place. However, instead of stopping at the tidal locking point, the atmospheric thermal tides, essentially bulges in the atmosphere caused by solar heating, pushed the planet past equilibrium and into backward rotation. This process involves what researchers call a thermal tide torque. As the Sun heats Venus's dense atmosphere, it creates regions of varying pressure. These pressure differentials generate forces that can affect the planet's rotation. On Venus, these thermal tides appear to have overpowered the Sun's gravitational tides, creating conditions for retrograde rotation. Kane's research illuminates how Venus's atmosphere essentially dictates its rotation. If Venus lacked its dense, fast-moving atmosphere, it would likely be tidally locked to the Sun, Kane notes, highlighting the atmosphere's crucial role in Venus's rotational behavior. What makes this finding particularly significant is that it represents a completely different pathway to retrograde rotation than the catastrophic collision theory. Rather than requiring a single dramatic event, the atmospheric tidal coupling model suggests a gradual process occurring over billions of years, a subtle yet persistent force slowly reversing the planet's spin. Evidence supporting this hypothesis comes from multiple sources. Computer simulations of Venus's rotational evolution show that atmospheric tidal forces could generate sufficient torque to overcome solar gravitational tides. Additionally, Venus's current rotation rate appears relatively stable, suggesting an equilibrium state between these competing forces. Further supporting this theory is the observed relationship between Venus's rotation period and its orbital resonance with Earth. Venus presents nearly the same face to Earth each time the planets make their closest approach, a pattern highly unlikely if Venus's rotation were solely the result of a random impact event. These findings transform our understanding of planetary dynamics throughout the cosmos. The James Webb Space Telescope will observe many exoplanets located close to their stars, worlds likely to be tidally locked. Venus serves as a crucial model for understanding how atmospheres might influence rotation rates of distant worlds and potentially create conditions different from what basic gravitational models predict. Venus is waving both arms around saying, "Look over here." Kane emphasizes, highlighting Venus's importance as a test case for models of exoplanetary systems. Without accounting for atmospheric effects on rotation, scientists might misinterpret potential climates and surface conditions of planets orbiting other stars. This atmospheric hypothesis doesn't necessarily contradict the impact theory entirely. An ancient collision may have altered Venus's original rotation, while atmospheric forces subsequently modified it further over time. The two mechanisms could have worked in sequence or together to produce the peculiar rotation we observe today. What's elegant about the atmospheric tidal coupling explanation is that it connects Venus's rotation directly to its most distinctive feature, its incredibly thick atmosphere. Rather than requiring separate explanations for Venus's rotation and atmospheric development, this theory suggests they are intrinsically linked, with each influencing the other through a complex feedback system. For planetary scientists, Venus's rotation demonstrates how assumptions about planetary behavior can be upended by unexpected mechanisms. Venus reminds us that atmospheres are not passive features, but active participants in planetary evolution, capable of fundamentally altering a world's most basic behaviors. The climate connection. Beyond altering Venus's rotation, its atmosphere creates the most extreme climate in our solar system. The connection between Venus's peculiar spin and its furnace-like conditions raises a profound question. Did one cause the other, or are they both symptoms of the same planetary evolution? The relationship between a planet's rotation and its climate is fundamental yet often overlooked. On Earth, our 24-hour cycle creates predictable heating and cooling patterns that drive weather systems, ocean currents, and atmospheric circulation. These patterns distribute heat from the equator toward the poles, moderating temperature extremes and creating habitable conditions across much of the planet. Venus presents an entirely different scenario. Its extraordinarily slow rotation means that a single point on the Venusian surface remains in sunlight for the equivalent of 117 Earth days before experiencing an equally long night. This prolonged exposure acts like a cosmic oven, continuously baking the surface and allowing temperatures to build to extraordinary levels while preventing efficient cooling on the night side. The thermal inertia of Venus's dense atmosphere somewhat mitigates what would otherwise be even more extreme temperature variations between day and night sides. However, this slow rotation fundamentally alters how energy moves through the planetary system, creating circulation patterns that would be unrecognizable to Earth meteorologists. One of the most critical consequences of Venus's rotation pattern is how it interacts with the greenhouse effect. The slow spin concentrates incoming solar radiation on the day side for extended periods, maximizing the energy absorbed by carbon dioxide and other greenhouse gases. This concentrated heating amplifies the greenhouse mechanism, contributing to the staggering 92 times Earth's atmospheric pressure at Venus's surface. This pressure creates physics we rarely encounter on Earth. Near Venus's surface, carbon dioxide behaves less like a gas and more like a supercritical fluid with properties of both liquids and gases. This state further enhances heat transfer and retention across the planet's surface, contributing to the remarkably uniform temperature distribution despite the extremely long day-night cycle. What's particularly fascinating about Venus's climate system is how disconnected the atmospheric circulation is from the surface rotation. The upper atmosphere circulates at speeds reaching 360 kilometers per hour, completing a full rotation around the planet every 4 Earth days. This superrotation means the atmosphere spins approximately 60 times faster than the surface below it. Imagine a raging river of gas that wraps around the entire planet while the ground beneath barely moves. The mechanics of this superrotation represent one of the most puzzling aspects of Venus's climate. Solar heating creates rising air currents that should form circulation patterns similar to Earth's. However, Venus's slow rotation prevents these traditional patterns from forming. Instead, Venus develops a unique circulation system dominated by 2 enormous vortices at each pole. These massive storm systems help drive the planet-wide superrotation while creating bizarre weather patterns unlike anything observed on Earth. The thermal tide, the atmospheric pressure wave generated as the atmosphere heats up on the day side, becomes a dominant force in Venus's circulation, overwhelming what would typically be the influence of the Coriolis effect. The disconnect between atmospheric and surface rotation also affects how heat is distributed. Measurements from various Venus missions show remarkably little temperature variation from equator to pole at the surface, only about 5 degrees Celsius difference. For comparison, Earth can experience temperature variations of over 100 degrees between equatorial regions and poles. Venus's uniformity results from the efficient heat distribution by the superrotating atmosphere, which acts as a heat transfer mechanism independent of the surface's slow rotation. The atmospheric composition tells part of the climate story. Venus's atmosphere is 96.5% carbon dioxide with a small amount of nitrogen, 3.5%, creating the most powerful greenhouse effect in our solar system. The thick clouds of sulfur dioxide and sulfuric acid droplets that shroud the planet reflect about 75% of incoming sunlight back to space, yet paradoxically contribute to the extreme surface heating by preventing infrared radiation from escaping. Climate modeling studies suggest that if Venus rotated at a rate similar to Earth's, its atmospheric circulation would be dramatically different. Faster rotation would establish distinct circulation patterns that could potentially distribute heat more efficiently. Some models indicate that a faster rotating Venus might have developed a less extreme greenhouse effect, potentially allowing for temperatures below the critical threshold where water can exist as a liquid. The feedback loop between rotation and climate on Venus creates a self-reinforcing system. The slow rotation allows for extreme heating, which drives the atmospheric dynamics, which in turn influence the planet's rotational evolution through atmospheric tides. This interconnected system has locked Venus into its current state, making it challenging to determine which factor, rotation or atmospheric composition, was the initial trigger for Venus's evolution into the inferno we observe today. What makes this particularly intriguing is that Venus receives only about twice the solar radiation that Earth does. Not enough by itself to explain the dramatic differences. The runaway greenhouse effect, amplified by the rotation pattern, pushed Venus over a critical threshold. Once surface temperatures rose enough to vaporize any existing surface water, that water vapor added to the heating effect, creating a cascade that transformed the planet. The implications of this relationship between rotation and climate extend beyond Venus. As we discover thousands of exoplanets around other stars, understanding how rotation affects climate becomes crucial for identifying potentially habitable worlds. Many exoplanets, particularly those orbiting red dwarf stars, are likely to be tidally locked, with one side always facing their star. Venus provides a valuable case study for understanding how Venus's lost oceans. Venus's story isn't just about what it is now, but what it once was. Beneath that suffocating blanket of carbon dioxide lies evidence of a profound transformation, from a water world with conditions potentially suitable for life to the scorched planet we see today, and its backward rotation may hold the key to understanding this catastrophic evolution. The notion that Venus, our toxic twin, might have once resembled Earth seems almost unimaginable given its current state. Yet compelling evidence suggests this hellish world once harbored vast bodies of water. Venus sits just within the inner edge of our sun's habitable zone, the region where liquid water can theoretically exist on a planet's surface. This positioning suggests Venus may have had the right conditions for surface water during the solar system's early days. Imagine standing on the shores of a Venusian ocean billions of years ago, gentle waves lapping at your feet under a cloudy sky, while distant volcanic islands, the horizon. This vision of Venus as a balmy water world isn't mere fantasy, but a scenario supported by scientific evidence. Scientists have detected evidence of an ancient ozone layer in Venus's atmosphere, a feature typically associated with planets that have substantial water and oxygen. This atmospheric signature points to a dramatically different past environment, one far more reminiscent of Earth than the Venus we know today. The most compelling evidence comes from chemical signatures locked in Venus's atmosphere. When spacecraft measured the deuterium to hydrogen ratio in Venus's clouds, they made a remarkable discovery. Deuterium, a heavier version of hydrogen, persists in the atmosphere, while regular hydrogen escapes more easily to space. The significantly elevated levels of deuterium compared to regular hydrogen reveal that substantial quantities of water once existed on Venus before being lost to space, essentially leaving behind a chemical signature of ancient oceans. This chemical evidence aligns with theoretical models suggesting Venus could have supported oceans covering up to 80% of its surface, an Earth-like water world in our own cosmic backyard. What drove such a dramatic planetary transformation? The relationship between Venus's rotation and its lost oceans represents a fascinating chapter in planetary evolution. Venus's rotation rate fundamentally altered how energy was distributed across the planet's surface, creating devastating consequences for any surface water. When a planet rotates at a moderate pace like Earth, heat is distributed relatively evenly. The planet doesn't have time to become extremely hot on the day side or extremely cold on the night side. However, as Venus's rotation slowed, each point on the surface began experiencing longer periods of direct sunlight, followed by equally long periods of darkness. This slow rotation created extreme temperature gradients between the day and night sides. On the day side, prolonged exposure to solar radiation would have gradually heated any surface oceans to their boiling point. The resulting water vapor was then pushed high into the atmosphere, where solar radiation could break water molecules apart, allowing the lightweight hydrogen to escape into space, while oxygen remained to react with surface materials. This loss mechanism accelerated as Venus's rotation continued to slow, creating a devastating feedback loop. As water evaporated, it contributed to greenhouse warming, which further heated the surface, causing more water to evaporate. Meanwhile, the slow rotation prevented the planet from developing climate regulation mechanisms found on Earth, such as the Coriolis effect, which helps distribute heat and create stable weather patterns. The timeline of Venus's transformation aligns with theoretical models of its rotational evolution. Early in its history, when Venus likely rotated more rapidly in a prograde direction similar to Earth, conditions would have been most favorable for liquid water. As its rotation began to slow and eventually reverse due to the combined effects of tidal interactions and atmospheric forces, the planet's water gradually disappeared. Scientists believe this transformation occurred over 1 to 2 billion years, with Venus transitioning from a potentially habitable world to its current state through cascading climate effects, all triggered or exacerbated by its unusual rotational pattern. How will we uncover the full story of Venus's watery past? Confirming these theories remains challenging due to Venus's hostile surface conditions, but upcoming missions aim to gather more definitive evidence. The Venus Spectral Rocket Experiment studied Venus's atmosphere using ultraviolet light, specifically targeting data related to the planet's water history. Meanwhile, the proposed Russian Venera spacecraft, scheduled to launch around 2024, will conduct remote sensing observations and deploy a lander designed to survive on the surface long enough to gather critical data. NASA's Da Vinci and Veritas missions and the European Space Agency's Envision mission, all planned for the late 2020s and early 2030s, will gather unprecedented data about Venus's interior structure, surface features, and atmosphere dynamics. They aim to further investigate the planet's past water presence and how its rotation affected its evolution. These missions could help resolve whether Venus once had plate tectonics similar to Earth, another factor influenced by rotation rate and critical for maintaining a stable climate suitable for life. If Venus did have tectonic activity early in its history, when its rotation was more Earth-like, it could have maintained a carbon cycle that prevented the runaway greenhouse effect that eventually transformed the planet. Understanding how rotation affects a planet's ability to maintain habitable conditions is crucial as we discover thousands of exoplanets around other stars. Many exoplanets, particularly those orbiting red dwarf stars, are likely to be tidally locked, with one side always facing their star. Venus provides a valuable analog for understanding how unusual rotation patterns influence planetary climate systems and the potential habitability of worlds beyond our solar system. For Venus, this rotation-climate connection proved catastrophic. As its spin slowed and eventually reversed, the once habitable conditions disappeared. The planet's current state, with surface temperatures hot enough to melt lead and atmospheric pressure 92 times that of Earth, represents the end result of this transformation. Earth's rotation warning. Earth's story shares an unexpected connection with Venus through a subtle astronomical phenomenon happening right now. Our planet's rotation is gradually decelerating at a rate of approximately 1.7 milliseconds per century, an imperceptible change to human experience, yet potentially significant over geological timescales. This slowdown isn't random or mysterious. It results primarily from tidal forces as the moon exerts a gravitational drag on our rotating world. This deceleration might seem inconsequential, but it raises a sobering question. Could Earth eventually experience a Venus-like transformation if its rotation continues to slow? After all, we now know planetary rotation and climate are deeply intertwined, with Venus serving as the extreme case study of how rotational changes can contribute to environmental catastrophe. The moon's gravitational pull creates tidal bulges in Earth's oceans that transfer angular momentum from Earth to the moon. This process simultaneously slows Earth's rotation and pushes the moon into a slightly higher orbit, a well-understood cosmic dance that has profound implications for our planet's stability. Unlike Venus's dramatic rotational change, Earth's deceleration is tempered by various stabilizing factors. Most crucially, our planet possesses something Venus lacks, a substantial moon. The moon serves as a cosmic anchor that steadies our planet's spin, providing a remarkable stabilizing effect on Earth's axial tilt and rotation rate. This celestial partner prevents the dramatic wobbles and shifts that could otherwise occur, while Venus drifts through space without such protection. The importance of this stabilization cannot be overstated. Without the moon's steadying presence, Earth's axial tilt could experience chaotic variations, potentially swinging between extremes that would create wildly unpredictable and possibly uninhabitable climate conditions. Venus, lacking such a companion, has been more vulnerable to external forces that altered its rotation. Earth's rotational properties directly influence our climate systems. The 24-hour cycle drives atmospheric circulation patterns, ocean currents, and weather systems that distribute heat around the globe. This efficient distribution maintains habitable temperatures across much of Earth's surface, rather than the extreme temperature differentials seen on slower rotating bodies. Ocean currents depend on the Coriolis effect, a direct consequence of Earth's rotation that deflects moving flows differently in each hemisphere. These currents function as global thermal regulators, transporting heat between equator and poles. Any significant change in rotation would disrupt these patterns, potentially altering climate zones worldwide. Earth's rotation also generates our protective magnetic field. As our planet spins, its liquid outer core creates electrical currents through a dynamo effect. This process produces the magnetosphere that shields us from harmful solar radiation that likely contributed to stripping Venus of its water and transforming it into the hellscape we observe today. Throughout our solar system, faster rotating planets generally generate stronger magnetic fields. Jupiter, with its approximately 10-hour rotation, boasts the strongest planetary magnetic field. Earth's 24-hour rotation supports our robust magnetic shield, while Venus, with its glacially slow 243-day rotation, lacks significant magnetic protection. This magnetic shield represents one of Earth's most crucial life-supporting features. Without it, charged particles from solar winds would gradually strip away our atmosphere's lighter elements, including water vapor. This process likely contributed significantly to Venus's transformation, as hydrogen molecules from water vapor were lost to space. Even with dramatic rotational slowing over millions of years, Earth has several advantages that would help prevent a Venus-like fate. Our greater distance from the Sun provides a larger margin of safety against runaway greenhouse effects. Additionally, Earth's carbon cycle, whereby carbon dioxide is absorbed by oceans and converted into rock, helps regulate our atmospheric composition over long timescales. The comparison between Earth and Venus reveals how planetary stability depends on factors creating profound differences in outcomes. Earth's larger size grants it stronger gravity, allowing it to retain lighter atmospheric elements more effectively. Our planet also experiences plate tectonics, which recycles carbon and helps maintain atmospheric balance, a process apparently absent on Venus. Current scientific consensus suggests Earth's rotational slowing poses no immediate or even long-term threat to planetary habitability. The deceleration rate is so gradual that in 100 million years, Earth days would be only about 25 hours long instead of 24. This rate allows natural systems ample time to adapt. Plants and animals would experience no meaningful disruption from such incremental changes, and climate systems would adjust gradually rather than experiencing catastrophic transitions. Earth would require billions of years to approach Venus-like rotation rates, far longer than the remaining lifespan of our Sun. While rotational changes influence climate, the relationship involves numerous feedback mechanisms. The presence of oceans, which Venus lacks, provides Earth with enormous thermal inertia that moderates temperature fluctuations. This oceanic buffer would help mitigate climate effects from rotational changes over long periods. Understanding these rotation-climate relationships has become increasingly important as we discover exoplanets around other stars. Many potentially habitable exoplanets orbit red dwarf stars so closely that they're likely tidally locked, always showing the same face to their star. These worlds present rotation scenarios more extreme than anything in our solar system, creating unique climate challenges. Venus and Earth thus offer crucial comparative case studies for understanding how planetary rotation influences habitability throughout the galaxy. While Venus followed a path to environmental catastrophe partly influenced by its rotation, Earth's more moderate rotational properties, combined with stabilizing factors like our moon and magnetic field, have helped maintain conditions suitable for complex life. Mercury's magnetic mystery. While Venus lacks a magnetic field entirely, Mercury presents scientists with a different kind of puzzle. The Messenger mission revealed something that defies our standard models of planetary magnetism, a magnetic field that covers just 10% of Mercury's surface. This anomalous configuration has forced scientists to reconsider fundamental assumptions about how planetary magnetic fields form and function. Mercury's magnetic field functions like a patchy shield, protecting only a fraction of the planet rather than enveloping it completely. According to conventional understanding, planets should either generate global magnetic fields that envelope their entire surfaces or have no significant field at all. Even more striking, this partial field isn't symmetrically distributed, but instead shows a significant offset toward Mercury's north pole. When Messenger's instruments mapped Mercury's magnetic field in unprecedented detail, scientists were confronted with data that didn't fit their models. The spacecraft's measurements revealed that the field strength is approximately 1% that of Earth's, substantially weaker than would be expected for a planet with Mercury's composition. The field's offset positioning created an asymmetrical protection pattern that provides significantly more coverage in Mercury's northern hemisphere than its southern regions. This configuration contradicts our standard understanding of planetary dynamos. The classical model suggests that magnetic fields are generated through the motion of electrically conductive fluids in a planet's outer core, driven largely by the planet's rotation. As these conductive materials move, they create electrical currents that generate magnetic fields with predictable patterns and distributions. The planet's rotation presents another contradiction. Mercury completes a rotation in 59 Earth days, extraordinarily slow by planetary standards. This sluggish spin should make it difficult to generate the internal motions necessary to sustain any magnetic field at all. Earth's much faster 24-hour rotation helps drive the convection currents in our planet's outer core that produce our robust magnetic field. Mercury's snail-paced rotation should theoretically be insufficient to power similar dynamics. Mercury's magnetic anomaly influences the planet's exosphere, the extremely thin layer of gases surrounding it. Scientific analysis has identified a distinctive two-peak distribution of sodium within this exosphere that correlates with the magnetic field's unusual structure. This pattern reveals how the unusual magnetic configuration directly shapes Mercury's tenuous atmosphere, with solar wind particles being deflected along specific pathways determined by the field's geometry. Looking beneath Mercury's surface provides crucial clues to this magnetic mystery. Mercury's internal structure differs dramatically from other terrestrial planets, with its core accounting for an astonishing 85% of the planet's radius. This proportionally massive core, primarily composed of iron, suggests Mercury underwent significant differentiation early in its history, allowing heavier elements to sink toward its center. For a magnetic field to exist at all, Mercury must maintain a partially liquid outer core that can conduct electricity and flow in patterns that generate the dynamo effect. The fact that Mercury possesses any magnetic field suggests its iron core has not completely solidified and still harbors enough thermal energy to sustain convection, despite the planet's relatively small size. The unusual composition and structure of this oversized core likely explains Mercury's magnetic anomalies. Rather than generating a field through mechanisms identical to Earth's, Mercury's dynamo might operate through alternative processes that produce its peculiar partial field. The core's disproportionate size relative to the planet's mantle could create unique thermal and fluid dynamics that result in the observed north-shifted magnetic field. This possibility has significant implications for our understanding of planetary magnetic fields throughout the solar system and beyond. If Mercury generates its field through mechanisms different from those operating in Earth's core, we may need to expand our models to account for a wider range of dynamo processes than previously recognized. Mercury essentially tells us that our understanding of how planets generate magnetic fields remains incomplete. The physical consequences of Mercury's partial magnetic field are dramatic. Without comprehensive protection, the planet's surface is more vulnerable to the solar wind, the stream of charged particles continuously flowing from the sun. In regions where the magnetic field is absent or weak, these particles can directly impact Mercury's surface, triggering processes that release atoms into the exosphere and potentially altering the planet's surface composition over time. This interaction creates a feedback loop between Mercury's magnetic field, the solar wind, and the planet's surface and exosphere. The variability in the sodium exosphere correlates with changes in the interplanetary magnetic field's intensity, highlighting how Mercury's weak magnetic protection makes it particularly sensitive to changes in the solar environment. When considering Mercury alongside Venus, we see two contrasting approaches to magnetic protection. Venus lacks any significant intrinsic magnetic field, leaving its atmosphere directly exposed to the solar wind. Mercury, meanwhile, maintains its partial field despite having almost no atmosphere to protect. These different configurations demonstrate the diversity of magnetic field generation among the inner planets, challenging us to develop more comprehensive models that can accommodate this range of behaviors. The existence of Mercury's partial magnetic field, despite theoretical reasons it shouldn't exist, reminds us that planetary systems often defy our expectations. Just as Venus's backward rotation challenges models of planetary formation, Mercury's magnetic anomalies suggest that planetary dynamos may be more varied and complex than our current understanding allows. Exoplanet implications. The planetary anomalies we've explored in our own cosmic backyard cast a profound shadow over our exoplanet discoveries. While scientists have identified thousands of worlds within their star's habitable zones, Venus teaches us that a planet's position alone reveals only a fraction of the habitability story. The rest might hinge on factors we can barely detect from afar. Astronomers increasingly recognize that rotation rates and magnetic fields serve as critical indicators when evaluating an exoplanet's potential to harbor life. A planet's spin directly influences how heat distributes across its surface, determining whether temperatures can remain stable enough to maintain. Liquid water, the universal solvent that enables life as we know it. Fast rotation, like Earth's, creates moderate day-night temperature differences and drives weather systems that distribute heat from equator to poles. Meanwhile, a robust magnetic field serves as a planetary shield, deflecting charged particles from stellar winds that would otherwise strip away atmospheres molecule by molecule. Unfortunately, these crucial habitability factors remain largely invisible to our current detection methods. When astronomers announce the discovery of an Earth-like exoplanet, they're typically referring only to its mass, radius, and orbital distance, properties we can measure relatively easily. The underlying assumption often goes unstated, that these worlds rotate and generate magnetic fields similar to Earth. But Venus and Mercury stand as stark reminders that such assumptions can lead us astray. What if the secrets of Venus hold the key to identifying truly habitable exoplanets among the thousands we've discovered? Consider the challenges of detecting an exoplanet's rotation. At distances measured in light years, discerning a planet's spin requires extraordinary observational precision, similar to trying to detect the subtle wobble of a spinning top from across a football stadium. Current techniques attempt to capture brightness variations as different surface features rotate into view, but this demands both exceptional light-gathering power and remarkable stability from our telescopes. Alternatively, scientists analyze spectral lines for Doppler shifts that reveal rotation speeds, measuring how light stretches or compresses as different parts of the planet move toward or away from us. These methods remain at the edge of our technological capabilities, working only for the largest, brightest exoplanets under ideal conditions. The James Webb Space Telescope represents our best hope for characterizing exoplanet rotation in the near future. Its unprecedented sensitivity and spectroscopic capabilities might finally allow astronomers to detect the subtle signals of planetary rotation, particularly for larger worlds orbiting nearby stars. Until then, our picture of exoplanet habitability remains incomplete, with rotation rates largely confined to theoretical models rather than observational certainty. Detecting exoplanetary magnetic fields presents an even greater challenge. On Earth, our magnetic field arises from the movement of molten iron in our planet's outer core, a dynamic system powered partly by our planet's rotation. This magnetic dynamo generates a protective bubble that shields our atmosphere from the solar wind. Without it, Earth might look much more like Mars or Venus, with its atmosphere severely depleted by constant bombardment from charged particles. Future missions may detect exoplanet magnetic fields indirectly by observing their interactions with stellar winds, similar to how aurora on Earth mark the collision between our magnetosphere and particles from the Sun. Such observations would be revolutionary, allowing astronomers to distinguish between truly Earth-like worlds with robust magnetic protection and those that, like Venus, may have lost their atmospheres despite appearing otherwise habitable. The exoplanets we've discovered often fall into categories based on limited observational data. We speak of super-Earths, mini-Neptunes, and hot Jupiters as if these classifications tell us everything about these distant worlds. Yet Venus reminds us how misleading such categorizations can be. If an alien astronomer observed our solar system from across the galaxy, Venus might appear tantalizingly Earth-like in terms of size and mass. Only by detecting its aberrant rotation, missing magnetic field, and toxic atmosphere would they recognize its true nature. Tidally locked exoplanets, especially common around red dwarf stars, provide a fascinating case study in how rotation affects habitability. These planets always present the same face to their host star, much like the moon does to Earth. One hemisphere experiences perpetual daylight, while the other remains in eternal night. Venus offers valuable insights for understanding these worlds. Its extraordinarily slow rotation creates conditions that parallel those on tidally locked planets. By studying Venus's atmospheric circulation patterns, scientists can better model potential climates on tidally locked exoplanets, including whether atmospheric circulation might moderate temperature extremes enough to permit habitability. Red dwarf stars host many of our most promising exoplanet candidates. Their small size makes planet detection easier, and their longevity offers ample time for life to potentially develop. However, planets in their habitable zones orbit so closely that tidal forces typically lock their rotation. The absence of a magnetic field compounds these challenges. Red dwarf stars produce frequent, powerful flares that would bombard nearby planets. With radiation, without magnetic protection similar to Earth's, these worlds would likely experience significant atmospheric erosion over time. Our quest to find truly Earth-like worlds must therefore extend beyond the traditional habitable zone concept. A more sophisticated approach would account for rotation rates, magnetic field presence, atmospheric composition, and numerous other factors that collectively determine a planet's true habitability potential. The planetary anomalies in our solar system are crucial calibration points for interpreting exoplanet observations and avoiding overly optimistic assessments of habitability. This perspective enriches our understanding of exoplanet diversity and complexity. Each new world we detect represents another data point in our evolving comprehension of planetary systems. Venus and Mercury stand as cautionary tales against simplistic habitability models. Their anomalous features remind us that planets are complex systems where seemingly small differences in fundamental properties can cascade into dramatically different outcomes. The next generation of telescopes must aim to characterize exoplanets more thoroughly, measuring the very properties that Venus and Mercury have shown to be crucial. While our telescopes scan distant stars for habitable worlds, a fleet of sophisticated spacecraft is preparing to investigate the most perplexing planet in our own system. After decades of scientific debate about Venus's backward rotation, we stand at the cusp of a new era in Venusian exploration that promises to unlock some of our nearest neighbors' most persistent mysteries. The upcoming missions to Venus represent a technological key that will unlock a cosmic vault containing secrets held for billions of years. 3 complementary spacecraft, Defies, Veritas, and Envision, form an unprecedented scientific campaign targeting our nearest planetary neighbor. Despite Venus's proximity and similarity to Earth in size and mass, it has received surprisingly little attention. Together, these missions will provide a comprehensive view of Venus's composition, structure, and evolutionary history. Defies will focus on atmospheric chemistry and surface imaging, while Veritas will map Venus's surface in unprecedented detail. Envision, a European Space Agency mission with NASA contributions, will examine atmospheric and surface processes. Each spacecraft carries instruments specifically designed to investigate Venus's interior structure, data crucial for understanding how the planet's rotation evolved over time. Their radar mapping capabilities will penetrate the thick Venusian clouds to reveal surface features that may bear geological signatures of ancient impacts or tectonic processes related to its rotational history. Atmospheric sensors aboard these spacecraft will analyze the complex dynamics of Venus's atmosphere, revealing how atmospheric tides interact with the solid planet. These measurements will provide critical evidence to evaluate competing theories about Venus's retrograde rotation, particularly the atmospheric tidal hypothesis. The combined datasets will allow scientists to model Venus's moment of inertia, a crucial measurement that could reveal whether a massive impact altered the planet's rotation early in its history, or if gradual processes drove the change. These Venus-bound missions draw crucial technological inspiration from other planetary exploration efforts, including NASA's Europa Clipper mission to Jupiter's moon Europa. The Europa Clipper exemplifies how missions to seemingly unrelated worlds contribute to a shared toolbox of exploratory capabilities. It will carry 9 scientific instruments and a gravity experiment, creating a comprehensive scientific platform to investigate Europa's subsurface ocean, which contains more water than all of Earth's oceans combined. The Reason radar experiment aboard Europa Clipper will peer through Europa's icy shell, technology similar to what Venus missions will need to penetrate our sister planet's mysterious interior. The Europa imaging system will capture detailed surface images with resolution vastly superior to previous missions, establishing new standards for planetary imaging that Venus missions will build upon. Similarly, the Thermal Emission Imaging System, ETHEMIS, uses principles that will help future Venus missions map thermal anomalies beneath the planet's thick clouds. The high-resolution mapping capabilities of the Venus missions could identify ancient stress patterns in the planet's crust that record its rotational evolution, essentially reading Venus's rotational history directly from its surface. Surface features oriented in particular directions or distributed in patterns inconsistent with the current rotation could provide definitive evidence for when and how Venus's rotation changed. While studies of Venus and Europa serve different immediate scientific objectives, they share fundamental connections through their investigation of planetary anomalies. Europa's subsurface ocean exists in a radiation environment that would seem prohibitive to life, while Venus maintains backward rotation against what standard planetary models would predict. These exceptions to expected planetary behavior provide profound insights into fundamental cosmic processes. The scientific return from these missions will unfold gradually as data is collected, transmitted across space, and analyzed by international teams of researchers. Initial results may emerge shortly after observations begin, but comprehensive understanding will likely develop through the mid-2030s as scientists integrate measurements across instruments and missions. Researchers currently beginning their careers may be the ones to finally resolve the Venus rotation mystery using data from these missions. For planetary scientists, these missions represent the culmination of decades of advocacy for returning to Venus with modern instruments. The scientific questions they aim to answer have persisted since the earliest observations of Venus's anomalous rotation, with new hypotheses developing as our understanding of planetary processes has evolved. The upcoming exploration campaign will transform Venus from a planetary anomaly into a key reference point for understanding how terrestrial planets evolve along dramatically different trajectories despite similar starting conditions. Beyond resolving specific scientific questions about Venus, these missions will contribute to our broader understanding of planetary systems throughout the galaxy. As we continue discovering exoplanets around other stars, insights from Venus will help scientists interpret distant worlds that might appear superficially Earth-like, but could harbor Venus-like conditions. The techniques developed to study Venus will inform future exoplanet characterization efforts. The investment in these Venus missions reflects recognition that planetary anomalies often prove more scientifically valuable than textbook cases. Venus's backward rotation and extreme climate make it a natural laboratory for testing planetary models and understanding how small differences in initial conditions can cascade into dramatically different evolutionary outcomes. By studying Venus, the exception rather than the rule, scientists gain insight into the full spectrum of planetary possibilities. The planetary exception principle. The upcoming Venus missions won't just solve a rotation mystery. They'll challenge a fundamental assumption in how we practice planetary science. Throughout scientific history, the most profound discoveries have emerged not from confirming what we expect, but from explaining what we can't. Those persistent anomalies that force us to rebuild our understanding from the ground up. Science advances most dramatically when confronted with exceptions to established rules. When Galileo observed Venus's phases through his telescope, the discovery contradicted the geocentric model of the universe. Similarly, the unexpected precession in Mercury's orbit couldn't be explained by Newtonian physics, eventually leading to Einstein's theory of general relativity. Today's planetary anomalies serve the same function. They act as powerful catalysts for scientific breakthroughs, forcing researchers to develop more sophisticated models that account for observations that don't fit existing frameworks. Consider how anomalies across our solar system have consistently pushed science forward. Mercury's unusual magnetic field challenged scientists to reconsider how planetary dynamos function. Standard models predicted either no magnetic activity or a global field similar to Earth's. Instead, Mercury presented an asymmetric field covering just a fraction of its surface. This contradiction necessitated completely new models of core dynamics and planetary evolution. Mars presents a compelling case with its methane mystery. The detection of methane in Mars's oxidizing atmosphere created a fundamental contradiction. In such an environment, methane should quickly break down unless constantly replenished. This anomaly sparked research into potential geological processes and biological activity. The investigation led to the development of the salty seal theory and refinements to Martian atmospheric chemistry models. What began as an unexplained phenomenon has transformed into a driver of scientific innovation. Saturn's rings further illustrate this principle with their surprisingly bright appearance, contradicting expectations for structures constantly bombarded by space debris. These rings should darken over time, yet they maintain a pristine appearance. This contradiction led to the pollution resistance mechanism theory, which proposed that high-velocity impacts vaporize incoming material, with Saturn's magnetic field subsequently removing charged particles. This mechanism suggests the rings could be billions of years old despite appearing youthful, challenging earlier assumptions about their recent formation. The discovery of Europa's subsurface ocean fundamentally changed our understanding of habitable environments. Before this discovery, liquid water was expected primarily on planets within narrow habitable zones around stars. Europa's ocean demonstrated that habitable environments could exist in unexpected places, dramatically expanding our search parameters for potential life throughout the galaxy. Computer simulations developed to explain Venus's retrograde rotation have revolutionized our understanding of planetary dynamics. These models incorporate factors previously considered secondary, such as atmospheric tidal forces and their long-term effects on planetary evolution. What began as an attempt to explain one planet's peculiar behavior has resulted in tools that provide insights into how planets throughout the universe might evolve under different conditions. The methane anomaly on Mars has transformed how we approach planetary atmospheric chemistry. The search for an explanation has led to improved models that integrate complex interactions between atmospheric gases, surface materials, and potentially biological processes. These sophisticated approaches now inform how scientists interpret atmospheric compositions on exoplanets, demonstrating how a single anomaly can enhance our broader understanding of planetary systems. Scientific models gain strength when they evolve to explain exceptions. The history of science shows that breakthrough moments come from investigating phenomena that challenge existing explanations. When Newton's laws couldn't account for Mercury's orbital precession, Einstein developed general relativity, a theory that explained the exception and transformed our understanding of gravity, space, and time. These planetary anomalies reveal connections between seemingly unrelated phenomena. Venus's rotation, initially viewed as an isolated peculiarity, now appears connected to its atmospheric dynamics, climate evolution, and potentially its early habitability. These interconnections suggest deeper patterns in planetary development that extend beyond individual worlds. This principle, that exceptions often reveal underlying patterns, applies across scientific disciplines. In biology, the discovery of extremophiles surviving in hostile environments revolutionized our understanding of life's adaptability. In physics, unexplained patterns in elemental spectra led to quantum mechanics. Similarly, planetary anomalies serve as windows into deeper cosmic principles that might otherwise remain hidden. Dr. Lindy Elkinstanton of NASA has noted that planetary anomalies demonstrate the limitations of Earth-centric assumptions. By studying worlds that deviate from Earth's patterns, we gain perspective on which features might be universal constants and which represent just one possible configuration among many. This approach helps scientists develop more flexible models of planetary evolution applicable across diverse cosmic environments. The revolution in exoplanet research further illustrates the value of understanding anomalies. As we discover thousands of new worlds, the lessons from our solar system's exceptions provide crucial context. Venus and Mercury serve as cautionary tales against simplistic habitability assessments based solely on a planet's distance from its star. Scientists now incorporate factors like rotation rates, magnetic fields, and atmospheric dynamics, lessons learned directly from studying our solar system's anomalies. The willingness to follow evidence where it leads, even when it contradicts established thinking, represents the essence of good science. Planetary anomalies provide natural experiments that test the boundaries of our scientific models. When observations don't match predictions, the solution is to develop better theories that encompass them. As we explore our solar system and beyond, we'll encounter more planetary exceptions. Rather than viewing these as obstacles, scientists recognize them as opportunities, natural experiments that reveal how planetary systems work under different conditions than Earth's. Each anomaly helps construct a more complete picture of cosmic processes, inviting us to embrace the unknown as the frontier of discovery. Our exploration of Venus's rotation has revealed a profound truth. The universe rarely conforms to our expectations. As we've seen, Venus challenges us with its atmosphere-driven rotation, reminding us that even neighboring worlds harbor fundamental mysteries. Venus teaches us to anticipate complexity when studying distant exoplanets. Stephen Kane's insight reveals the atmosphere's fundamental role, a much more integrated part of the planet that affects absolutely everything, even how fast the planet rotates. Transformative scientific breakthroughs emerge from investigating anomalies that reveal deeper truths. What cosmic mysteries do you think will redefine our understanding next? Join the conversation as we continue exploring these